Désolé des ennuis informatiques du pauvre Alexandre. Juste pour vous l'introduire, donc Alexandre Solon a fait sa thèse à ce qui s'appelait l'Université Paris 7 il y a quelques années avec Julien Tailleur. Il a beaucoup travaillé sur les systèmes actifs. Il a fait en particulier des articles qui ont eu pas mal d'impact sur la définition de la pression dans un système actif et pourquoi parfois on n'arrive pas à définir la pression dans un système actif. Après, il a été fellow à MIT pendant quelques années. Et il est revenu au CNRS et il est au laboratoire de physique théorique de la matière condensée à Jussieu, qui, du temps de Françoise, s'appelait le laboratoire de physique des liquides, où il continue à travailler sur les transitions de phase dans les systèmes actifs. C'est quelque chose qui, pour moi, est un peu derrière tout ce qui se passe dans les condensats biologiques. Alors, c'est des systèmes un peu différents dont il va parler, mais ça me paraît très, très relié. Donc, c'est pour ça que je souhaitais absolument qu'il fasse un séminaire. Il a accepté. Merci, Alexandre. Et à toi.
Merci beaucoup, Jean-François. Donc, je vais parler en anglais, comme c'était prévu. So, good afternoon, everybody. So, if you have followed previous lectures of Jean-François, you know that in active matter, you have many different kinds of collective behaviors. And actually, a good part of them can be understood as phase separation. So that's what I want to discuss today. So here are the kind of systems that I have in mind. We have bird flocks. Here you have actin filaments in a motility assay, so they are driven by molecular motors attached to a plate, and they form these density waves that are moving with a periodic pattern. Here you have a colony of bacteria that are growing and making these patterns of low and high densities. And here you have a bacteria called Myxococcus, in some conditions, aggregate, so that many cells aggregate to form a fruiting body. So you could tell me already, how is it phase separation? The phase separation we are used to, as polymers, for example, is a kind. So if you wait and you let your vinaigrette separate, you have two macroscopic domains separated by a well-defined interface. So of course, these are very different. They are biological systems. It's more complicated. But what I want to show is that there are some kind of variations around the phase separation. And in the simplest theoretical description that we have to understand these systems, they are ultimately phase separation. So what kind of system I will be talking about? So active matter composed of self-propelled particles. So each particle consumes energy to move. And so these particles move I will take the simple model where they move at constant speed. And then they reorient their direction of motion. There can be different mechanisms. Here are two popular kinds. So you can have run and tumble bacteria that move in straight lines. And then at some tumble event, they choose a new direction at random. So that's what bacteria like E. coli do. You can have active Brownian particles that move persistently but reorient with rotational diffusions. And self-propelled Janus colloids do this kind of trajectories. And then on top of that, I will add interaction. If I add repulsion, like short-range steric interaction, you can get motility-induced phase separation, or MIPS for short. If instead you have alignment between the direction of motion, you have collective motion or flocking. So these are the two types of phase separation. Actually, for flocking, I will explain why it's phase separation. So the two types of behaviors that I want to talk about today. So usually I would give a seminar either one or the other, but yeah, we talk about both. I hope it's not too dense, but please stop me if it's going too fast. So let me first explain the mechanism that leads to motility-induced phase separation. So as I said, it comes from self-propulsion and steric repulsion. So you have your particles moving around, and if they collide, because they are persistent, they will try to keep moving into each other, and they are just blocking each other, so they can't move for some time. And if they stay blocked for long enough, other particles come, they aggregate, and you see that even more particles are going to come and aggregate, and that leads to a phase separation. So this is an image from a simulation, and you get large domain with high density coexisting with a gas at a lower density. So it's a mechanism that gives you a cohesive state, this phase separation, but without any attractive force, just from self-propulsion and repulsion.
Why don't they rotate and go away from the cluster?
At some point, they will rotate and go away. But
So your mechanism assumes that the rotation is slower than the time it takes to aggregate new particles?
exactly, they have to be persistent enough for this mechanism to operate. Otherwise, you don't have phase separation. Excuse me?
If they are big, they are not broad, and they do not rotate. If they are big,
They can have other sources of noise, like a bacteria. It's quite big, but they are, like the flagella can disentangle and they rotate because of that. It doesn't have to be thermal noise. Okay, so you get phase separation between a dilute phase where the particle moves fast and a dense phase where they move slowly. And here are some examples of that. With self-propelled colloids, here are two different kinds of colloids. The Mycococcus bacteria I've already shown. Here it's fire ants on a plate who form this aggregate where they get dense and stop moving. So the question I want to ask is rather obvious for a phase separation, is how do we understand the phase coexistence? So you have two densities in the gas and the liquid. How are they controlled? Because here we are out of equilibrium, so we cannot play around with the free energy that we would minimize to understand the phase coexistence. So what do we do instead? Well, we have to turn to continuum equations that describe the dynamics of the system. And to do that, actually, the model with steric repulsion is not convenient because we don't know how to do a good coarse graining to write continuum equations. So I will consider a slightly different model that's called quorum sensing model, where the steric repulsion is replaced by a velocity that depends on density. So concretely, particles look how many other particles are around, and they adapt their velocity according to this function v of rho. That is a parameter of the model. And if this velocity is decreasing, it mimics the effect of the collision, that is to reduce the speed of the particles. And if you simulate this model, you see the same kind of phase separation. With this model, by rather standard techniques, you can write in a gradient expansion the equation for the dynamics of the density field. Here is the only relevant field since we have no alignment. And it looks like this, so it's conserved dynamics. And this m is a mobility coefficient, and then you have the gradient of this term that depends on the local density rho. And these two gradient terms who are important at interfaces. Here are just the expression for the coefficient that we get from the microscopic model. So we have called this a generalized Canillard equation, and it's actually very similar to the passive Canillard equation because it has the same terms, it's just the coefficient in front of the interfacial terms are more general. Actually, the passive Canillard equation corresponds to lambda equals minus kappa prime over 2, because it's the special case when the dynamic can be written as the gradient of the derivative of a free energy function. But in the general active case, you cannot write it like that. Then from this equation, we can understand the phase diagram quite well. So what do? We consider that we are in the steady state with a very large system. So we have two macroscopic phases with gas and liquid. And so we want to understand how to compute the densities in these two phases. So in steady state, we know that the current has to be 0. So this quantity in blue has to be constant. And you can evaluate it in the two phases. It already gives you an equation that's the equality of chemical potential. That's true for the passive and the active system. Then we need a second equation to set these two densities. And in the passive, this second equation, actually, it's a condition that tells you that a front exists that can link the gas to the liquid phase. And in the passive case, where this mu can be written as the derivative of free energy, it turns out that the second condition is, of course, the equality of pressure, with pressure defined in the usual thermodynamic way. In the active case, you don't have this property, but what we have found is that you can define an effective density, so it's just a change of variable that, as far as we know, doesn't have much physical meaning. So it's a function r of rho, with r defined here as a function that with a definition that involves the lambda and kappa terms. And with this r, we can write it at the derivative of a free energy with respect to this new variable. So we are able to define some kind of generalized pressure, which is not the mechanical pressure, but it's a quantity that will be equal in the two phases. And we can go further, define a generalized free energy density. And the phase coexistence then is set by minimizing this generalized free energy density. So we can then compare with what we obtain if we simulate this quorum sensing model. So I remind you, particle moves with this function v of rho. And here I take this function and I plot the phase diagram as a ratio of v0 over v1, which quantifies the activity, and as a function of density. And the different dots are different kind of simulation with non-untable particles, active Brownian particles. And the red line is what we predict. So it works quite well. It deviates at large activity, and we know that it's because the gradient expansion that we use breaks down at large activity. If you can compare with the black line here, which is what you get if you neglect the interfacial term. So it means you assume that you're in equilibrium somehow, and you compute it without using this effective density. And you see that it works. There is a significant difference. And here the dashed line is the spinodal line.
What's the interfacial tension between the two?
Oh, I will come to the interfacial tension soon. It's an interesting question. So for now, we have the same, we have a very conventional phase separation with the same phase diagram as Jean-François has shown you in the lectures just before. Except one difference is that here the interfaces are important for the phase diagram. So that's very different to what we are used to in equilibrium, where the interface makes a negligible contribution to the free energy and has no effect on the phase diagram. And so here it does. So then the next step is to look at what happened in a finite system. So now we consider a finite drop, and we take into account the curvature of the interface. And in particular, we compute the difference in pressure between the droplet and the outside gas, so the Laplace pressure. And here I plot it for the quorum sensing model as a function of the radius of the droplet. And we find the usual result, that it goes like 1 over the radius. But now if we go back to the first model where we had only steric repulsion between particles. Actually, it becomes very different because the Laplace pressure is negative. So that's something that was measured for the first time in this paper. And they call that a negative surface tension. So you should not have the thermodynamic interpretation of surface tension that interfaces will proliferate. Here is this, we just want to say that this Laplace pressure is negative, so it corresponds to a negative surface tension in that sense. Okay, sorry. I have to get my daughter at daycare. No, it's fine. I can go late. Okay, sorry. So it's quite different, and it's actually not explained by the generalized Canillard equation that I've shown you just before. So we need a more refined description. Actually, a solution came from this paper from the group of Micates, where they consider a more general equation. So it's actually the same that we had before, but in addition, they have a noise term, and this term in red that you cannot write as the gradient of the mu that we had before. And now it's the most general equation that you can write at this order in gradient, so I will not keep adding more and more terms. But with this one, it's enough. For some choices of parameters, now you have a negative surface tension. And what they show is that it leads to a reversed Ostwald ripening. So if you have a big bubble and a small one, contrary to what happens in the passive case, they tend to equilibrate their size. What this leads to, if you simulate the equation, you see this kind of thing with a phase separation. You have a gas and a liquid domain, and inside the liquid, you see bubbles of gas. So they've called that a bubbly phase separation. And here we are not in the coarsening phase, it's a steady state. What happens dynamically is that new bubbles are nucleated inside the liquid, and then they move around, they get bigger when they merge with others, and at some point they reach the boundary outside and they get expelled in the outside gaze. But is it really what we see in this model with steric repulsion? Because actually people have been stimulating this model for many years and they have never seen that. So that's the question that we ask, and actually, yes, that's what you see, but you need very large system to see it. Here it's system with 1.6 million particles, and you start to see clearly this bubble dynamics inside the liquid phase. But still, to study this bubbly phase separation, we chose to consider instead a lattice model that is easier numerically, but that has the same ingredients, self-propulsion and rotational diffusion and some isotropic diffusion. And you see the same thing, but just more clearly. And it's easier to compute many things in this phase-separated state. In particular, we look at the statistics of the bubbles that you see here. And here I plot the number of bubbles of area A, so as a function of area, just normalized by the total area of liquid, which is proportional to the system size. And what you see is that it's power law distributed. Here it's log-log scale. It's power law with a cutoff. The cutoff is moving when the system size increases. So that with other measured quantities, we have interpreted this result as this kind of phase separation is like a self-organized critical system. If you want to make the analogy with the usual sand piles model, so the grain of sand that you add to your sand pile would be the new bubbles that you nucleate. Then you have avalanche dynamics that makes a bubble with a power law distributed size. And the open boundary condition here is played naturally by the phase separation. So you have a kind of self-organized critical liquid. Importantly, here the coefficient is the coefficient here of the power law. Alpha is smaller than 2, around 1.75. And that means that if I keep increasing the system size, the total area of gas inside the bubbles will diverge. So something has to break down at some point. And here is what happens. If I start from a density such that the outside gas is very small, I increase the system size, it gets smaller, and I increase it even more, and it completely disappears. And when you reach this point, you don't have any more the open boundary condition of self-organized criticality. And at this point, you reach a distribution of bubbles that do not depend on system size anymore. So you have actually a microphase separation because you can define a characteristic bubble size that is independent of the size of the system. Okay, so that's what I wanted to tell you about MIPS. So you have a phase separation, rather classic, because we can even define effective thermodynamics to understand the phase diagram, with the only difference that the phase diagram depends on the interface. But on top of that, you have negative surface tension that gives you a reversed Ostwald-Rippling, a bubbly phase separation, and ultimately this self-organized critical phase coexistence and a large, very large scale microphase separation.
So do I understand correctly that the effective thermodynamics is only with a mean field theory?
It is a mean field theory, yes. Because
after when you study the effect of negative surface tension, is no longer compatible with thermodynamics.
Well, it still predicts the coexisting densities. I mean, you have corrections from the Laplace pressure.
These bubble dynamics you would not have in...
No, you don't have the bubble dynamics, for sure. But like the density inside the bubble and the density in the liquid here are still predicted by this same theory.
Is it exactly accurate, or is it a slight difference?
The difference is that since you have many small bubbles, the corrections due to Laplace pressure will be more important. Yes. Okay, if there are no more questions, I will switch to the second topic, which is about flocking. And by flocking, I mean many individuals moving together, doing collective motion. So, for example, sheep, to change from the birds. Here you have cells moving together to fill the gaps in wound healing. Here you have vibrated discs that are asymmetric, and when you vibrate them up and down, they start moving collectively. And here an example of swarming robots, with which you have, of course, a lot of control on interaction, and you can do many things. So as before, we are physicists, so we want to understand the basic physics. We look at minimal model of this, which has self-propulsion and an alignment interaction. And one such model that we have proposed with Julien Tailleur in 2013 is called the active easing model. So it's a lattice model with no excluded volume interaction. So you can have as many particles as you want on the lattice. And the particle carry an easing spin. The plus move, the sign of the spin gives you the direction of self-propulsion. So the plus spin moves to the right, the minus spin moves to the left, and on top of that, you have symmetric diffusion in all directions. And you have alignment. So the alignment is just a ferromagnetic interaction with rates that you could have in a passive system controlled by your temperature. So that's what we see in this model. So here I show the phase diagram as a function of temperature and the density. And at high temperature, you get a disordered gas. here I show the profiles average along the vertical direction. So the density is in blue and the magnetization in green. It fluctuates around 0, it's disordered. At low temperature or high density, I see an homogeneous liquid and now here the magnetization is positive. And in between, we see a phase separation between a disordered gas and an ordered liquid. So this liquid phase is moving inside the gas. Here is how it looks in 2D. You have these large bands that are moving inside the gas. So it has all the characteristics of phase separation. You can see nucleation or spinodal decomposition, depending on where you are on the phase diagram. You can see hysteresis. You have the lever rule. The position along the horizontal line gives you the fraction of liquids. So everything that you have in the usual phase separation. So it's the same game as before. We're still out of equilibrium. So how do we understand the phase coexistence? We write continuous equations. And for this kind of lattice model, it's very standard to write this equation. You get the dynamics of the density and the magnetization field. So they both have a diffusion term. Here they have an advection term in the horizontal direction of self-propulsion. And in blue here, it's the usual 5-4 alignment term. The only thing a bit unusual is this here, this term R over rho. It means that the ordering temperature depends on density. And that's something, even if you don't find it in your equation, we've shown that they're always generated by the noise, quite generally. Then we need to look for phase-separated solutions. But now, as I've told you, the liquid is moving. So we need to switch to the co-moving frame at a speed c. And c, in general, is not the self-propulsion velocity v. Actually, it's usually faster than the self-propulsion. So we have three unknowns, the densities in the two phases and this velocity. And okay, I spare you a lot of detail, but you find a unique phase-separated solution that fixes these three quantities uniquely. So we are happy. We have this solution that allows us to understand, not quantitatively, but to understand the phase separation in our active easing model. But actually, we find other solutions that are either solitons like that or periodic, and you have many of these solutions. You have solutions with all different periods and spaces between the peaks. So, well, we don't see this solution in the active easing model, but actually, they are important for another model. It's quite famous, the Vicek model, introduced in 1995 by Vicek and collaborators. So I remind you how it works. It has the same ingredients, alignment and self-propulsion. So particles compute the mean direction of their neighbor, and they align with this direction with a small noise, eta, and then they move in their new direction of motion. So for a long time, actually, in the paper by Vicek and collaborators, they described the transition between the disordered and ordered state as a ferromagnetic order-disorder transition, and they saw a continuous transition. So this phase diagram. But what we realized from what we have learned from the active easing model is actually that the phase diagram is like that. So you have the disordered gas, you have the ordered liquid, but in between you also have a region of phase coexistence. But just now the phase coexistence looks different. You get a microphase separation. You have this train of bands that are moving, so they are ordered, the bands, and they're moving together, and you get this periodic these periodic patterns. But you still have phase separation. You still have the lover rule. If you are the fraction of liquid now is related to the number of bands in the system. So what's the difference from the point of view of the continuum equation that leads to having phase separation or microphase separation? Actually, it's not obvious because, well, here I've put the same equation as before. For the V-check model, you have different ways of writing continuous equation, but just to prove my point, I will just generalize this equation to the symmetry of the V-check model. That is, instead of having a scalar magnetization, now you have a vector. And the advection now goes in all directions of space, so you have a divergence and you have a gradient. But otherwise, I just take exactly the same equation. So if I look for stationary solution, I get exactly the same ones because they are invariant in the vertical direction, so it's exactly the same problem. So what's the difference? Well, actually, the good solution must be selected by the fluctuation. Since they have the same deterministic solution, the fluctuations must be important. And to show this, we have simulated both equations, so with scalar magnetization and vectorial magnetization. We start from a large phase-separated solution, and we let it evolve for a very long time. And for the scalar magnetization, we see that it remains the same. For the vectorial one, you see that the fluctuations are quite different. There are the giant density fluctuations that you maybe you've heard about. And this breaks down the phase separation and leads to this microscopic, this microphase separation. So the fluctuations really select the good. I mean, they select one or the other solution. Okay, so to recapitulate about this transition to collective motion, it can be understood as a liquid-gas transition, except the phase diagram is a bit different. Maybe you've noticed. We don't have a critical point because this would be forbidden. You would be going continuously from a disordered gas to an ordered liquid. So they have different symmetry. You cannot go continuously from one to the other. And what happens is that the critical point is actually sent to an infinite density. So you can never cross continuously. But otherwise, you still have binodals and spinodals, and it's still a phase separation. And so on top of that, you have different types of phase coexistence, which is controlled by the symmetry of the interaction. So of course, I've said it's a bit more complicated. It is more complicated in experiments where you have other ingredients. But you kind of see these two different solutions. In the experiments on actin, you see a kind of microphase separation. And here it's an experiment that is done in a group of Denis Bartolo with colloidal rollers. And they see very large bands of this colloid when they are moving in a channel like that. So to conclude, so I wanted to talk about both problems because they have a bit both the same story, that they show all the hallmarks of phase separation. So you can have spinodal decomposition or nucleation depending on where you are in the phase diagram. You have hysteresis, the lover rule, so that's the vinaigrette that we are all used to. But on top of that, you have things that are, you have the spice, things that are more specific to active matter. And so this bubbly phase separation that turns to a microphase separation at large scale. And in both cases, you see that it's not captured by a mean field theory, and the fluctuations are essential in understanding these phase separations. So this work comes from actually many papers with many co-authors that I won't read all the names, but you can read them here. And I thank you for your attention.